Hello and welcome to the next part of this video series where we attempt to prove the existence of Euler's number, or E. In the previous video, we established that an arbitrary term in the sequence 1 plus 1 over n to the power n is always less than or equal to the sum from k equals 0 to n of 1 over k factorial. That is, the sum from 0 to n of the reciprocal of factorials. Now, in this video, what we're going to attempt to do is actually bound this summation itself. So we're going to attempt to bound the summation that I'm circling in red by something else, which is a bit easier to work with. Now, we're going to first notice that k factorial is greater or equal to k squared for all k in naturals and k greater or equal to 4. So at first this observation may seem contrived, but it should make sense later when we actually make use of this to bound this series circled in red above. So we can prove this using MI. The base case is easy to establish. 4 factorial, which is 24, is indeed greater or equal to 4 squared, which is 16. So let's assume the inductive hypothesis, that is, k factorial is greater or equal to k squared. We have to use this inductive hypothesis to show that if we assume the inductive hypothesis, we can prove that the inequality holds for the next natural number. So how do we do this? Well, let's assume the inductive hypothesis. We can then multiply both sides by k plus 1. Now, if we can show that this part, this underlined expression, is greater or equal to k plus 1 squared, then we show that k plus 1 factorial is also greater than k plus 1 squared, simply because if a is greater or equal to b and b is greater or equal to c, then a is greater or equal to c. Okay? So our aim now is to prove the part of the inequality that I've just bracketed in green. We want to prove this part of the inequality. And we notice that the left-hand side of this inequality can be expanded out like this, and the right-hand side like this. So we can cancel x plus 1s, and we get x squared is greater or equal to k plus 1. Geometrically even, this is quite easy to see. All it's saying is that the parabola, the order 2 polynomial with a vertex at the origin, is greater or equal to k plus 1, which looks like this, for k is greater or equal to 4. We see that they intersect, actually, at 1 plus root 5 over 2, which is actually Euler's, not Euler's number, sorry, which is actually phi. They intersect at phi, and after that, the order 2 polynomial begins to take over, and it grows faster than y equals x plus 1, or y equals k plus 1 in this example. That's not a proof, but it's just sort of like an intuitive reason why k squared is indeed greater or equal to k plus 1 for k is greater or equal to 4. If you want to, you can also prove this inequality with induction. This one over here, the one I'm circling in red, you can prove this by induction. It's pretty simple. You should be able to do it. So I'll sort of just assume that this inequality is true because it's pretty easy to prove. Okay. So just use induction to prove it. So we've proven this inequality, which means that the bracketed part of the inequality above is true, which means that we've indeed proved that k plus 1 factorial is greater or equal to k plus 1 squared by the transitivity of inequalities. A is greater or equal to b, is greater or equal to c, means a is greater or equal to c. Alright, so hopefully that should make sense, and we've proved this inequality. Now, why did we prove that inequality? Why is it useful? Well, notice that we proved k factorial is greater or equal to k squared, or k is greater or equal to 4. What that means is that the reciprocal of 1 of k factorial is less than or equal to the reciprocal of 1 over k squared. There's many ways of explaining why this is true, but you can see it for yourself. Essentially, if we have something like 7 on this side, which is greater than 4, then and we divide 1 into 7 parts, then the parts are going to be smaller than if we divide 1 into 4 parts. So hopefully that should make sense, because we're dividing 1 into more parts. So this inequality holds. Now, why is this interesting? Well, if this holds for k is greater or equal to 4, then the sum from k equals 4 to n of 1 over k factorial is indeed less than or equal to the sum from k equals 4 to n of 1 over k squared. But remember, in the previous page, we were concerned with the sum from k equals 0 to n of 1 over k factorial. It turns out there's no problem there. If we want to consider the sum from k equals 0 to n, we just add the previous 4 terms. So the first term is 1 over 0 factorial, which is 1. The second term is 1 over 1 factorial, which is 1. The third term is 1 over 2 factorial, which is 1 over 2. And the fourth term is 1 over 3 factorial, which is 1 over 6. And we just add that to both sides of the inequality. All right, great. So we have bounds now on the sum from k equals 0 to n of 1 over k factorial, which is it's less than or equal to the sum from k equals 4 to n of 1 over k squared plus 2 plus a half plus a sixth. So this still seems hard to work with and ugly, but we're going to make this even nicer with some calculus. Now, this trick I use is not actually a trick, because we're not using circular reasoning here. The only thing we're going to use is that the derivative of x to the r is equal to r times x to the power r minus 1 for integers in R. Remember, for integers in R. So we can actually prove this using the definition of the derivative for integers in R. That means R is equal to 1, negative 1, 2, negative 2, 3, negative 3, etc. We can prove this result for all integers without making use of the exponential function. For proofs of this for all real numbers, it can get a bit more complicated, and you may actually have to end up using implicit differentiation and the exponential function. But in this case, we can actually prove this result for all integers R without the use of the exponential function. So we're not assuming anything about the exponential function. Okay? Now, we want to somehow bound this expression over here. Alright, this is the expression we want to bound. So what we notice immediately is that 1 over k squared is what's called a monotonically decreasing function. So let's plot the function for some points. At 1, the function's at 1. At 2, the function is at a quarter. And it's a monotonic decreasing function. So it's a function that is decreasing, 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 decreasing. Now, what is the summation? What does the summation even mean graphically? Well, we notice, if I can just cheat a bit and say this is 4 over here, even though it's clearly not, and this is n, we notice immediately that this summation is equivalent graphically to the area of all these rectangles. You can see that. Alright, it's equivalent to the area of all these rectangles. Minus 1, dot, 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 dot. Alright, I'll just sort of color them in so they're more clear. It's equivalent to summing the area of all these rectangles, because the width of each rectangle is 1, and the height of each rectangle is a term of this series. And if we sum everything together, for example, this rectangle's area over here is in fact 1 over 4 squared. This area of the rectangle here is 1 over 5 squared. And all the way to 1 over n squared is this series over here, which we're so interested in. But we also notice something else. Because this is a monotonic decreasing function, these are actually Riemann sums, specifically lower Riemann sums for the integral from 3 to n of 1 over x squared with respect to x. They are by definition lower Riemann sums for this integral, because this is a monotonic decreasing function. Over each interval of this partition from 3 to n over here, this is a partition from 3 to n, over each interval of this partition, the function assumes a minimum at the right endpoint of each interval. So for example, at 3, 4, the function assumes a minimum at 4. So what we're computing is lower Riemann sums for the area under the curve from 3 to n of 1 over x squared. And this integral is easy to evaluate, because this integral is the same thing as the integral from 3 to n of x to the power negative 2 with respect to x, which we can evaluate using the power rule for differentiation, which I talked about earlier. So this integral is nothing but negative x to the negative 1, and bounds or limits of integration are from 3 to n. So evaluating that, we get negative n to the negative 1 minus 3 to the negative 1. Okay, and so writing this out in a nicer form, this is just 1 over 3 minus 1 over n. So now we can say for sure that this summation here is definitely less than or equal to 1 over 3 minus 1 over n, because this expression here is a lower Riemann sum. It's an under approximation. It's a lower Riemann sum. It's a lower Riemann sum for this integral over here, which we can actually evaluate using the fundamental theorem of calculus, which requires, by the way, no assumptions for concerning the exponential function at all. So we're not actually using circular reasoning. Now, going back over here, now that we know that, we can apply that bound, and we see that this is less than or equal to 1 over 3 minus 1 over n, which we've established. Again, plus 2 plus a half plus a sixth. Now this, if you add everything together, is actually equal to 3 minus 1 over n, which is obviously less than or equal to 3 for all natural numbers n greater or equal to 1. So we have some nicer bounds, much nicer bounds, for the terms of the sequence which we discussed earlier over here. So we know now that 1 plus 1 over n to the power n is less than or equal to the sum from k equals 0 to n of 1 over k factorial, which we've just shown over here, is less than or equal to 3 minus 1 over n. It's less than or equal to 3 minus 1 over n, which is definitely less than or equal to 3 for all natural numbers n. By natural numbers, I mean numbers 1, 2, 3, etc. Not including 0, obviously, because if we included 0, then this over here wouldn't make sense. So we proved that our sequence is definitely bounded above. 1 plus 1 over n to the power n is always less than or equal to 3. It's bounded above. Now, if we can just show that this sequence over here is actually monotonic increasing, if we can show it's monotonic increasing, then by the monotone convergence theorem, which we proved in the previous video, we can show that the limit as n approaches infinity of 1 plus 1 over n to the n exists. And thus, that e, which is defined as the limit as n approaches infinity of 1 plus 1 over n to the n, exists. So this is going to be the motivation for the next video, to show that 1 plus 1 over n to the power n is a monotonic increasing sequence. Thank you for watching.